Good morning. Today we'll be beginning our discussion on a brand new topic. Topic is stereochemistry. We will be on this topic for a little while longer, so this is going to be just an introduction into what is stereochemistry and what are the things associated that we must know before we learn it. But before that, let's look into what we've learned previously. Previously, we learned how to draw line structures and given a chemical formula, how to interpret the number of single, double, and triple bonds in that molecule, and using that knowledge, we learned how to name and draw isomers. Okay? That knowledge is very critical to actually having and developing a deeper understanding of stereochemistry. Without further delay, let's look into the topic. And what is the definition? I have paraphrased the definition, which is when you have a molecule that's three-dimensional, atoms are oriented in three-dimensional, right? How does the 3D orientation of atoms in a molecule affects before, during, and after a chemical reaction? Now you must remember and recall that chemical reaction is nothing but collision between molecules. Sometimes it's between two molecules that are 2D, or between molecules that are 3D, or between 2D and a 3D, or any other combinations you can think of. Stereochemistry specifically only concerns with molecules that are three-dimensional. Now let's actually switch back and go on a memory lane back to General Chemistry 1. Now if I had given this molecule, which is methane, and had you draw the structure, you probably drew something like this, and the decrypted code, you probably gave me this, and you determined the electron geometry is tetrahedral. Is there anything wrong with this picture? No. But however, if I show you something like this, you think, whoa, that looks different. Yeah, it sure looks different than the 2D model. That's because as humans, we see everything in 2D. When we go to a movie theater, the screen is basically 2D. The screen's flat. Everybody is on the screen. Nobody or nothing is coming out of the screen, which is why we need a 3D pair of glasses to see something that's designed 3D. Now, there's another piece of information is the bond angle between carbon and hydrogen is 109 degrees. Now, as it's written on the 2D format, you would think that the bond angle is 90 because that's just the way we drew it. But that's not the case. And you also notice three sets of bonds here. One that looks conventional, the solid line, but there's two that looks different. One is called the closed wedge, another is called the open wedge. The closed wedge is the dark one, open wedge, as the name indicates, the broken one. So I have chosen a white background because when you're drawing something, you're most likely drawing it on a piece of paper. So I wanted to mimic the paper, so I chose a white background. Now the bond that's conventional, that somehow you'd always draw, it's on the plane of the paper. That means it's literally glued to the paper. The one that's closed wedge, that's the black one, it's coming in front of you from the paper as you're looking at it. Let's say you look at the paper from a top-down view. The two hydrogens that are conventional are on the paper. The front one is peeking straight at you, and the back one is going behind the paper. That's the open wedge. Okay? Now it's important because as we already established, stereochemistry revolves around three-dimensional molecules. But stereochemistry actually works around something that's very unique. It's called stereoisomers. We've learned the idea of isomers, but what are stereoisomers and how is that unique? Well, stereoisomers also are 3D molecules, but they have something unique than a 3D molecule shown above, like a methane. And methane is not a stereoisomer, it's a 3D molecule. But what makes it a molecule stereoisomer that's three-dimensional is chirality. That's the concept we're going to be talking a lot about in the next couple of weeks. Chirality means carbon is attached to 4 unique group or species. I've shown an example, a line structure, and of course I have exaggerated one of the carbon and shown them in highlight. Carbon I'm looking at is the one marked with the letter C in red. That carbon is attached to a methyl group on one side, it's attached to a hydrogen, it's attached to a Br, and through another carbon to another set of things, which is why I put it as a giant conglomerate. But the fact of the matter is, all you can say is that carbon has got 4 different things attached to it, right? So it is chiral. And chirality is a concept that's exclusive to carbons. That's interesting. Now, I don't want you to take any notes because all of this information is just it's a step to learn the concept better. And as you do problems, all of these actually will sink back in. We'll keep coming back to it. So there's no reason to memorize, no reason to panic or worry or any of that stuff. All right. Now, some of you might also be going down the road to take exams like MCAT or dental school exams where there will be organic portion. So attention to detail is very important. They might refer to a chiral carbon as a stereogenic center. So knowing how things are defined by different people under different circumstances is very critical. And also, chiral carbon is indicated by an asterisk. I've shown a different example this time around. Instead of putting the red C, I put the asterisk there just to indicate you that carbon is attached to 4 different things. Now, a molecule is considered a stereoisomer not only because it's 3D, but it must at least contain 1 chiral carbon. Remember, that's how we said stereoisomers are unique, is they have chirality, but they must also be 3D, so at least it must have 1 chiral carbon. Now let's shift our attention slightly, not too far but slightly. What's the relationship between a chiral molecule and light? The instrument you're looking at on the screen is called a polarimeter. Well, life would be a lot easier if each one of us have a polarimeter sitting next to us when we do our homework or take a test. But unfortunately, these things are expensive. So we must find an alternate way to understand whether a molecule is R or S, which is what we're getting into, is this particular instrument. If a molecule is chiral and it's 3-dimensional, can rotate a light clockwise or counterclockwise. If the molecule that's thrown in this instrument and if the light is rotated clockwise, it's called an R isomer. If the light is rotated counterclockwise, it's called S isomer. So ultimately, if you have no chiral carbon, then no RS, because no chirality means no stereoisomerism. No stereoisomerism means the molecules cannot be rotated by a light clockwise or counterclockwise. Now, this idea of rotation is very important because I want you to understand just because a molecule is 3D and just because it has chiral does not make a molecule what is known as optically active. A molecule is optically active for which it must first have chirality and it must also rotate the light clockwise or counterclockwise. I might quiz you. Optical activity, what does that mean? But there are special cases where a molecule is optically inactive despite the fact it's chiral, despite the fact it's 3-dimensional, it just cannot rotate the polarized light. So it must be chiral, it must be 3-dimensional, it must also rotate the light. If it doesn't do one, then it's optically inactive. It's important you understand this, okay? You can always go back and review these ideas. There's no reason to memorize anything. So, what's next? We have now established that when a light is rotating clockwise, it's R, and when it's rotated counterclockwise, it's S. But let's hold our discussion there for just a second because we need to learn something else under which this R and S would fit in. So we need to now go back and understand what the larger umbrella is. For that, we need to talk about constitutional versus conformational isomers. Now remember, I mentioned previously, right? Previously we learned how to draw isomers. Those are called constitutional isomers because what does that mean? We have learned this, we just didn't call it constitutional. Isomer generally means constitutional. You have the same chemical formula, just different structural arrangement. Okay? Now let me put something else just for comparison, then it actually makes more sense. Now, stereochemistry is about conformational isomers, not about constitutional. So whatever we learned up until we started stereochemistry is constitutional. Conformational Same exact formulae, and you look at these two structures. What is quite contrastingly different about this is on the top where it's constitutional, the Br is in a completely different carbon, right? Whereas in a conformational, it's on the same exact carbon, but on one structure it is coming out of the plane, that is behind the plane or back of the paper, and on the other one it is coming in front or in front of the plane, right? In front of the paper. That's conformational. That little difference makes a lot of difference. You might think that's very minor. No, that minor difference is a huge factor in drug manufacture, and that's something we're going to look at next as a practical example. So under conformational, there are 4 different kinds. We're not going to define and expand on these because first we need to learn how to do R and S. That's what we will be doing right after I finish what I want to say. Because if you don't understand how to do R and S, there's no point in going extensive detail on these 4. Once we understand R and S, we will come back and expand our discussion on each one of these so we actually know what value do these carry. Okay, so what's next? Okay, at this point we have established what chirality means in its simplest form, and we've also established there's something called R and S. But we have not learned R and S, and that's not the point at this moment. I want you to know there is something called R and S. We've established that, and how that can lead to various conformational isomers, which we have not talked about, but we have established what those are. So let me give you an example on where does the chirality, where does the idea of R and S, where does all this tie into? We can all relate to this. It's drugs, something we consume at least once in our lifetime to prevent something from happening or to cure something, right? One such case is a drug called thalidomide. In the 1950s, it was prescribed to pregnant women with morning sickness. Well, the drug was tested, had rigorous testing. It had no effect on the pregnant women, so it was prescribed in Germany. But babies were born with severe abnormality, and eventually the results were pointing at this drug. So it was eventually banned, and people were not allowed to buy it. So most drugs that we consume are racemic mixture. That means they contain a 50% R and a 50% S. Now typically only one is active, the other is inactive. The inactive might cause some minor side effects, but nothing crazy like in this case. So this is the structure of thalidomide. As you can see, it's an R and S. You may also see R sometimes shown as plus and S as minus. But R is the active. That was what designed to help the women. But the S is the inactive one that caused effect not on the women but the babies. So here's just a schematic sketch of how a drug typically works. Okay, if your drug is a racemic mixture, which is R and S, it's not always R is active or not S is always active. The R, which is active, has a perfect binding mechanism. You see the drug and whatever it's binding to has a perfect position, perfect placement. Everything is like a perfect lock and key. Whereas the inactive is not supposed to do that. It's purposely designed or purposefully part of the process where it's not supposed to do the job. And it's not always a problem. We take Tylenol, it may have a racemic mixture, we don't have extreme side effects, but in the case of thalidomide, it is. Manufacturers these days are actually producing exclusive or exclusive S depending on what would work best. Those things are a little more expensive and can be hard to find, but it is available these days. Okay, now with that all said, I can now get you into relate to why you learned this concept. Now we would actually get in and learn the concept of R and S. We need to first learn how to figure out whether something is R or S before we can go tie that concept back to the conformational isomers, and then eventually we'll do more things in the idea of stereochemistry. So what's next? By now we have established the idea of chirality, which means carbon attached to 4 different species, and also the effect of chirality in drug production, and then the stereoisomers R and S, where if the light spins clockwise it's R, if it spins counterclockwise it's S. But we won't have a polarimeter. We won't have a polarimeter in a lab. We won't have a polarimeter when we do our homework, quiz, or test, or just to learn the concept. All we have is a paper and a pencil. So how do we go about it? Well, there are some rules. And over the years, I've tweaked the rules to add some keywords to make them explicit. That makes life a lot easier. Those finer details normally get unnoticed or said in a different way, which in itself can add to some confusion. And at this point, I also want to take James from Mastering Chemistry for the table that he came with that I'll be using here. And that table makes also life a little easier along with the rules that I've tweaked. So without further delay, let's get started. What are the rules? First, you must determine which carbons are chiral, if any. If it is chiral, highlight each one with a star so you know which carbons you work with. You work with one carbon at a time. If you work with too many at a time, it's just going to make things chaotic, and chaos is never good. Second is priority. Now, this is the heart of the whole problem. Now, this is something you may have never come across unless you've taken an organic class before or you have seen these material before. So what are these priorities? This is where I said the rules are tweaked. The takeaway from the 2 bullet points that you're seeing is the first point of contact and then the atomic number. Generally, higher the atomic number, higher the priority for that species out of the 4 that you're choosing around the chiral carbon. Now, the first point of contact is even more important over the atomic number because that's the first thing you establish. Now, all of these would seem a little abstract. That's why I have a protocol problem here, because we are all visual creatures and we learn better with an example. So I have chosen the carbon that I'll be working with an arrow, and I've highlighted it with an asterisk. And I know that the carbon highlighted is attached to an H, an OH, and 2 carbon networks on either side, left and right. Let me say why. Let me put a C. Why did I call it carbon network? I didn't use any specific terms. I just call it carbon network because they're all also further attached to other things. Now, conventionally, it said higher atomic number, higher priority, but they don't mention the first point of contact. What that does is you just simply rank BR as number 1, and that's where you start your number 1. That's not true. You go by the first point of contact first. With respect to the highlighted carbon, it's attached to a H, NO, and 2 C's on either side. Based on the first point of contact alone, O wins the race on atomic number, so that gets 1. And then hydrogen is no rocket science, gets 4 because it's the smallest element in the periodic table. Between 2 and 3, the war is not won because they're both, that highlighted carbon that we're working with is attached to carbon on both sides. So the war is not won there. So we look further to what those carbons are themselves attached to, or what the carbon on the left's got 2 hydrogens, carbon on the right's got a Br and a hydrogen. Br is a higher atomic number over the hydrogens on the left, so that's where the war is won. And then the carbon on the right gets the second priority, carbon on the left gets the third priority because carbon is still bigger than hydrogen, which is in the number 4 spot. Now, using this table, it's premeditated. So if you connect 1, 2, 3, it's a clockwise rotation, right? So it's clockwise for CW. And where is the 4th rank substituent? It's in the back. So clockwise and 4th rank substituent is in the back. So the assignment for that carbon is an R. It is just that simple. So the takeaway from this is the first point of contact. If you do it the way I have done it, chances are you never make a mistake and you're making your life very, very easy. And second is the atomic number. Down the road, we will have some special cases, but we have to first get through this R and S and get through the conformational isomers before we come back to the special cases. And I know you probably think, can we have more few practice problems to work? Yeah, I'll do a few more practice problems and then we'll go from there. All right, so stay tuned. Okay, we worked out one problem just to understand the concept of R and S. Now it's time to do a couple more practice problems just to help you understand the concept even better. With that said, I have given 2 problems on the screen that you're looking at, and I'm going to work both of those because each one presents a different idea on how to do things.
Right? Now, something I probably didn't mention in the video, but I figured I would have eventually said it during another example, was if a carbon contains a double bond, that carbon cannot be chiral. Okay? So what I have done here is I went ahead and put an asterisk and a C on the carbon that I'm looking at, going to be working with. I might even put an arrow just like I was in the video. So this is what I'm focusing on. And I put a C here just to tell you that this carbon is attached to a double bond, so that can be chiral. This cannot be chiral because it's got 3 hydrogens. This is an oxygen, and chirality is exclusive to carbon. This is not chiral, that's not chiral, which leaves us with just that being chiral. Now, what did I say about first point of contact? This is the carbon we're interested in, right? Now, that's attached to a Br, a hydrogen, an oxygen, and a carbon. What do you think has the highest atomic number out of these 4 first point of contacts? You're right, it's the Br. So let me put a different color on there. Obviously, hydrogen's 4. What do you think is bigger between these two? C or O? O is bigger, so that's 2. And this would be 3. So you have to connect 1, 2, 3 in a sequential manner. So it'll be 1, 2, and 3. So that is sequential. Is that clockwise or counterclockwise? That's counterclockwise. That's correct. Counterclockwise. And this hydrogen, which is the 4th rank substituent, is in the back. So now go to the table, pick out counterclockwise and back. That's an S. So this chiral carbon is an S. Just that simple. Right? Let's look at the next example. So again, we're going to work with 1 carbon at a time. I'm going to highlight the carbon that I'm first working with. That's the chiral carbon, right? Because we have 2 chiral carbons, we're going to work with 1 at a time. Looking at this, this is the carbon we're working with. This is attached to carbon on one side, carbon on the other side, a Br one side and hydrogen on the other. With respect to this carbon, which of the first point of contact do you think has the highest atomic number? You're right, that's the Br, so that's 1. Hydrogen's obviously 4. Which of these two you think would take the second spot? Well, the water is not 1 here because they're both C's, but this C is attached to 2 hydrogen, but it's also attached to this entire network, whereas this is only attached to 3 hydrogens, right? Because this is also attached to this group extended network, which is why I call it network. This is 2 and that's 3. Now again, we connect 1, 2, 3, that's clockwise and it's in the back. So clockwise and back is clockwise, back is R. So this chiral carbon is R. Let's look at this one. Again, we're working with this chiral carbon, so let's highlight that. With respect to this, you have, again, C on both sides. You kind of guessed it where I'm going with this, right? So with respect to this, the first 4 point of contact, Cl gets the highest atomic number, so that's 1. This is 4. This would be 2 because of the same explanation I gave earlier. The C is attached to 2 hydrogens and also this entire network, whereas this is only attached to 3 hydrogens, so that's 3. So if we connect all of these, this is again counterclockwise and back, so that would be yes. And that's simple as that, right? Now, what I would recommend you is, you see how I used colors. Sometimes using different colors can really enhance your learning. So watch these 3 things first and understand what it is, and then work out the practice problems I'll give you, and then we'll take this topic further. All right? So let's keep our mind open.